Welcome to Happy Path Programming. I'm Bruce Eckel.
I'm James Ward. Welcome to Happy Path Programming. Today we have some friends who have been up in Crested Butte this week for the Rust Developer Retreat. And so we've been exploring some Rust stuff with some folks up here this week and been fun. So
Yeah, this is the last day of the retreat, and we've been diving in and out of Rust, and it's been kind of a new experiment because we've had camping on the porch and on the floor, and it's been sort of like glamping, I think, because we've had all the everybody brought food, and then we've been making meals and things like that. It's been pretty fun, and we've been diving into Rust a lot and using AI to write Rust examples, which has actually been really helpful.
yeah.
And
Bruce would continually say when we ran into a problem or didn't understand something, just feed it in a ChatGPT and see what it says. And we'd feed it code and say, fix this code, and then it would help us.
It would help us. Wouldn't always fix it completely, but it would move us forward. Sometimes it would get you unstuck. And also, when I've been interested in a topic, I would just say, give me an example that demonstrates this. And
Yeah.
again, didn't always get it right the first time, but it would certainly move you forward a lot. So it was very helpful to do that.
Yeah, and the project that I worked on mostly with participation from everyone here was around the Easy Racer thing, which is comparing different frameworks and languages for structured concurrency and different approaches there. So we'll get into that at the after we talk about just general stuff. So
Right.
before we go there, does anybody have anything they worked on, things they learned about Rust, things that were interesting, surprising, any highlights or worth sharing? Or just what you worked on, what you learned?
Yeah. What's your experience? What was your experience at the retreat? Just general stuff.
Yeah, well, this is Garden Weekly. I was the one camping in the porch, or I wouldn't exactly call that camping. I was sleeping in a tent. But, none of the other usual things with camping. But I came in. I had the skeleton of a little project something I wanted to do for a while. I'll just tell the story. I have a terabyte drive at home that has all these pictures of my kids back from the early 2000s when we had a series of different digital cameras, and they were downloaded by whatever weird software they had onto a hard drive on the desktop computer we had, and eventually all that got shoved off on this terabyte drive. And this thing's a real mess. There's multiple copies of photos. There are photos that have been resized. There are just multiple copies in different directories. There are photos that have been resized or rotated or whatever. And so I had this idea of it would be nice to have these photos organized. And the first thing is to get rid of all this duplication. So I had this basic idea for a thing that would just walk across the file tree and try to identify what files it thought might be duplicated. Sort of starting off with looking at file names and then doing a cryptographic hash of it. And so anyway, I just had the skeleton. I had a little bit of code, coming in. There's a bunch of stuff. I guess the main thing is like how super effective ChatGPT is at giving you help, and specifically Rust. I've used it for other languages, but man, it's super effective in Rust. That was really surprising. Bruce is now on a first name basis with ChatGPT. He just refers to it as Chat. So, I finished up basically yesterday. Finished up what I intended to do, which was doing searches across the tree, indexing things by their cryptographic hash, and indexing things by sort of partial matches on file names, and even started adding some tests because that partial match logic started getting complicated, and so got into a little bit of the testing, trying to figure out. We actually had this philosophical debate yesterday on mocking, because I was trying to mock out pieces of the file system stuff, and we got into a big debate. I actually eventually ended up abandoning mocking for that case, basically because of that discussion. But in any case, yeah, I mean, that was, I guess my impression is, not really having done much, before this week, is like, if you get code to run, it's going to, it's very likely to work, unless the one actual bug I had was forgetting a negation operator, a logical negation operator. And, everything else, there was none of this fooling around. There was none of this, I've got this dictionary of values. What do I name that key again? What are the types on the, whatever. It's like the compiler forces you to deal with all of that. Mm-hmm. And, and the only one-time errors I ever encountered were files that didn't exist. I'd forgotten to create my file system and stuff like that. But, for the most part, it's like, if you can get the code to compile, it's going to run and it's going to do what you meant it to. And, the process is frustrating because you have to make a lot of decisions up front, but, you pay that pain up front, and then getting your code to run is like anticlimactic because it's just like you've done all the hard work already. So, I mean, that's my overall impression.
Nice. And you were able to get something working and tested and made some good progress.
Still working through my tests. Again, I started making that the file name matching logic more complicated, and so that's just, honestly, it's right now my logic is messed up. I got to go back and look at it. But I've got a test suite, and I got this thing running, and it's at least what I had as of yesterday afternoon was essentially what I had set out to accomplish. So nice. That was pretty nice, and now it's sort of on to adding features and gold plating the crap out of this. The great thing about these things is lots of people had different ideas about doing image matching, like approaches to figuring out whether an image has been rotated, or rotated or resized or something like that, and really got a bunch of good research done on how I can approach that problem when I get to the point I want to tackle it. Mm-hmm. So it's great having a lot of people around, and I can just ask stupid questions like, explain this to me, and people are generally happy to explain it to you. So
nice. Yes. Yeah, well, that's cool. Nice to. Was there anything that stuck out in the Rust language that was new or interesting as you're in the language? And
I think the whole, it's the same thing everybody runs into. It's it's this whole concept of borrowing and understanding that Rust is really, really specific about ownership, and and that's one of the things you have to think about. There was one point where I was wrestling with some problem, and it was wanting me to change. Well, I mean, it was an error. I had to change something, and after thinking it through, it's like, well, I guess the quick way to fix this is just to clone this object, and which kind of hurt to do, but then I realized after thinking about it for a minute, it's like, well, this is the design choice I made, and I have to stare every time I look at this code. I have to stare at that clone thing, and it has to hurt me. And so eventually, it's either like I'm going to freak out over wasting the memory and go deal with that, or I just deal with the fact that it's like, well, I had to make a lot of copies of memory to make this thing correct.
Yeah. Yeah, I experienced the borrow checker, kind of the power of ownership. I was playing with in Tokio. There's a one-shot channel with a transmission channel side and a receive channel side, and in the one-shot channel you can only have one receiver and one transmitter, and it's kind of cool that the borrow checker actually enforces that. It's like, no, you can't share either of those in multiple places because that's not allowed, but the compiler can actually verify that, you actually, it won't compile if you try to share those references in multiple places. And it's
pretty brilliant.
Yeah,
and I think a lot of people come in and see the lifetime system as, it's so that we don't have to have a garbage collector. And what I've learned is that's only part of what it does. That's the one that you run into initially. But it also means that with Rust's generics, you don't have to have any annotations for covariance or contravariance like you do with JVM languages. And that is so nice. That is such a wonderful thing not to have to think about. And then there's some other things. Well, like concurrency, the lifetime system makes sure, it helps ensure that concurrency is correct as well, like the example that you gave there.
Yeah, the one I think my biggest pain point with Rust this week was mutability, because there's places where I've spent so much time just in the world of immutable that having to do some things with mutability and then fight through some of the challenges with that. I think there was one compiler we were struggling with where it's like, oh, you can't do this because it needs a mutable version of this, and you have an immutable version of this. And I'm like, if everything was just immutable, that would certainly simplify things. And I get for performance memory reasons why they use mutability in places, but definitely like felt the pain of that mixed world. And
but we've learned that even in pure functional languages, you sometimes have mutability. I mean, it's usually behind a wall. So
I think having done most recently a lot of Kotlin Scala, it's kind of intellectually painful to have to make things mutable. My first impulse after the last year or so has been training myself to try to do things immutably. But it's like you kind of have to suppress that and be like, yeah, this is a different language. And,
See, I had the exact opposite problem of Jim. So I come from a almost strictly Python background, and I am not big into functional languages. Not that I don't like it, I just have not had a lot of exposure to it. And so I was exploring creating a game using Rust this week. I'm kind of an amateur game dev, and that's an area where I was really struggling. I was like, okay, everything's mutable right now. We're just gonna, we're gonna pass these things around. Everything needs to mutate, et cetera, et cetera. And I was like, no, I feel like I want this to be immutable, but I'm not quite sure what the right way to do that is. So I had the opposite problem that you had, where you wanted everything wanted to be immutable, and I was like, no, everything feels like it needs to be immutable. And I'm struggling to find out where I can make things immutable. So that's been a struggle for me. But
it's an evolution.
Mm-hmm. Yeah.
But the interesting thing is that what I was running into is I had a function that was called from. It was actually an argument to another function, and then that function was working off of a data structure that itself at the very key core had a member field that had to be mutable, because that was the purpose of this function, was to go through and populate this data structure. And I spent some time wrestling around with that, because it was saying, this little function right in here, which is pretty deep into the call chain, is trying to modify this thing, which was declared way out here, and the compiler traces all the way through and said, nope, you have to flag this as a mutable function because you're mutating something. And it's really, 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 I think you would really have to work hard to try to subvert that, because it's just deep into the compiler that it's gonna check all that for you.
Yeah, it's very meticulous. So what were you working on, Duncan?
Okay, so let's see, I came to Rust writing Python extension modules. So NumPy and SciPy give a real performance boost to Python, but some algorithms can't be cleanly expressed in using that approach. And we had some success porting just the performance critical parts of some applications, some signal processing algorithms. So this week I've been thinking about using Rust for higher level problems like scientific programming in general and web applications. So I was looking at Axum, which is a web framework. And I've been trying to think about error propagation. Basically, there's a question mark operator, which I feel it should have a name. But the
Flat
question...
map.
That's what I was
Yeah.
thinking. It's effectively
Kind
a
of
flat
like a
map.
flat map.
Yeah.
But that really helps you to write code that's really clean, deal with get the domain logic. There's a single level of abstraction principle where you're trying to have everything at the same level of abstraction, and just with question marks, and then deal with all the errors at a higher level. And I was serving up a Svelte UI from Axum. I work a lot with single page applications, and so Rust and Axum and Svelte seems like an interesting direction.
Yeah. On the question mark operator, it is nice that it's more general than like in Kotlin the question mark is only on a nullable type. The fact that you, I think, can put a question mark on not just result but on option and other things, it can kind of chain onto multiple types. I don't know if it does that through a type class or.
Yeah, I went and asked chat about, what are the different ways to handle errors with result? And it listed a bunch of things, then it missed at least one thing, which I said, well, what about is error? Oh yeah, I forgot about that. But and there's a bunch of different ways that you can handle the result, but one of them, the cleanest way is the question mark, which extracts the success value, and then if there's a failure, it basically throws it out to doesn't throw it. That's the wrong word. It passes it out into the result of the function that you're inside of, and it just makes it really clean. It's really nice. And I guess if you were in Scala, it would be the for comprehension, and in Haskell, I think it's the do
notation.
Yeah, do notation, right? So it's picked up from that, but it's nice that they don't use any, functional. They don't mention anything about monads and all that kind of stuff because they don't want to go down that path. But when you look at it, you realize, oh, that's what it is. The result is a monad, and the question mark is basically a flat map, I think.
Yeah, I think I ran into some challenges with this where in the world of monads, you get into the whole thing of monad transformers where let's say you've got an option and a result and you need to kind of munge those two things together. That's where in the world of monads you then get into monad transformers and it gets all tricky. And I don't think that Rust had a direct way to do something like monad transformers. And so then you have to do some kind of manual unpacking and pattern matching, which gets a little bit nastier than I'm used to, but it wasn't too bad. The one really nice thing in Rust is not having exceptions, and and this is very similar to the way that I write code in Kotlin and Scala is putting the exception or the error into a data type. Like result in Rust, and that felt so much nicer than the world of exceptions.
Yeah, basically exceptions are side effects, right?
Yeah.
Yeah. So they're just like
yeah. So not dealing with exceptions was certainly nice.
Mm-hmm. Yeah, I was looking at because I've been looking at structured concurrency in Python, and so I was in particular looking at cancellation and seeing how Python, when you cancel something, it actually monitors. It puts the code in for you to monitor for cancellation and do all the necessary cleanup. So I was curious about how does Rust do that? How does it contrast it? And its cancellation system is, they call it cooperative cancellation. And it means that you actually have to you have to put in one of those one-shot channels, and then you have to look for somewhere in your task, you have to be looking for a cancellation signal. And then when that happens, you can return from it, or whatever it is that you want to do, so it's explicit. So Rust tends to be a lot more explicit in things, but it does, we did figure out that in the Tokio library, when we were using the select, it does, so what select does is it runs a number of tasks against each other. And the first one that succeeds, it returns as its result, and then the rest, it cancels. And it does do cleanup when it does that. So there is some automation, but also you have to be ready to do it yourself. Monitor for cancellation yourself in normal code.
Yeah. So anybody have any other thoughts or things they learned before we go into structured concurrency? Dive into that.
Yeah, I guess one point in the question mark operator, what came out of that was like, there is an error message around using that is actually one of the rare times. That one of the nice things is being somebody learning the language is the compiler gives you a lot of help. About 80% of the time, it's going to give you a hint as to what you probably need to do. And in this one particular case, you use the question mark operator in a function that doesn't return an option or result. The error message is a little confusing, but effectively that's what it's saying is you can't do this because you can only use the question mark operator in a function that returns option or result. And it kind of made me think of, with respect to concurrency, if you work in these languages that have async operators, you have the whole idea of what color is your function. And it's kind of the same thing, that you've got to decide, am I going to follow this normal error protocol? And if I do, then I can use things like shortcuts like question mark operator. If I don't, then you're stuck with some more manual way of handling stuff because you don't have a way to really propagate out those errors. So it's kind of the same situation. It governs how you design your functions because you have to think about how am I going to return errors? So what am I going to do if I get an error?
Yeah.
Right, and if the question mark produces an error that isn't basically the general idea is if it produces an error that isn't part of the signature of your return type, the compiler will say, oh, that won't work because you've told me that this thing returns this particular kind of error, and the question mark produces a different kind of error, so you have to go up and specify it. Yeah. So
the one tricky piece that we ran into and did figure out around this was if you've got a function that can fail in multiple different ways, how do you then put that into the error channel, the error type? And the way that I would do that in Scala is with a sum type that is a fails. Well, in our case, it was either a request error, so the request failed in some way, or a timeout error. And through an anonymous sum type, you can just say request error or timeout error. And it seems like there's an open proposal in Rust to add anonymous sum types to the language, but I don't think it's available yet. And so what we ended up doing was creating an enum to represent that sum type, but then we had to transform our error into that enum to represent that. So it was fine, but yeah, if there were anonymous sum types, it would have cleaned that up a bit.
Yeah, it's a pretty sweet feature. Python has it as well. And what about, does Kotlin have something like that?
Well, you would do it the same way that we ended up doing it with Rust with an enum or something.
Yeah, so I guess you call it an enum an explicit sum type.
Yeah.
Right.
Yeah. Cool. Yeah, so that part wasn't too bad. I mean, we were able to model our data structure fairly easily in the way that we wanted to. Yeah, the async support out of the box is definitely nice. And yeah, I don't know. I felt like the async stuff felt like a good approach, but pretty typical, I think, these days of the colored function approach of you need to indicate that this is async.
And we were able to get through all of the easy racer exercises.
Yeah.
At least with Tokio.
Yeah.
Which seems like the first library you should reach for, because Rust's philosophy is providing just enough in the core language, but not assuming that there's an operating system.
Yeah.
Which is really nice if you're working on hardware, like the interview that we did, I don't know, a year or so ago. They were able to put something on hardware that was using async and thus have shorter wake-up times and then longer battery life.
Yeah.
Well, okay, that's pretty neat. But their architecture has to be a little different to do that, and so you always have to go find a library. And there's not, like Python has the built-in async IO library, whereas Rust you have to choose a library. But the most common one is Tokio, but that assumes you have an operating system.
Yeah.
So building everything with that.
Yeah. I wanted to point out one of the other challenges that I had was the error messages are often really helpful, but as soon as we dove into the world of using macros in more complex ways, then some of the nice things that you usually get with the helpful error messages did fall apart a bit as we went into macro land. And that was specifically on the Tokio select macro. And I remember struggling through that a bit because the error messages all of a sudden weren't as helpful as they were when you're in non-macro land.
I think it depends on the macro writer. That was my impression. In other words,
get that. Could you try again?
It could be it could be
on the web.
It could be well done, but it requires the macro writer to know enough about it to but I could be wrong about that. Maybe it's just inherent.
Maybe the macro could do a better job at helpful error messages or something.
Right.
Yeah, and it was interesting to see in Tokio Select's case that they almost created like a DSL, and it's the first time I'd seen in Rust using a macro to create a DSL looking thing. But then the challenge with that is that whenever you're in kind of a DSL land, you're no longer in the normal land, and then I need more documentation, more examples, more assistance because I'm in kind of a little bit different of a world. And so I remember with Tokio Select kind of struggling with, what is this thing doing? It's not normal Rust code. So what do I do in this macro DSL land? And most macros that we use, whether println, whatever, don't have straightforward. They don't have kind of a DSL to it. But Tokio Select had a bit of a
that was kind of an eye opener because you realize it's possible to create a kind of a DSL inside of a macro. Didn't know that.
And I don't know how common that is in Rust beyond Tokio Select. Like if that's
first time I've seen
typical
it, but I don't have vast experience, so it could be a common thing that we just haven't seen much of.
And then the other thing we realized there was that as we were working through Easy Racer, so Easy Racer is a bunch of scenarios to test approaches to structured concurrency, and the basic ones say, okay, race these two things against each other, and Tokio Select is a really easy way to do that race. But we discovered when we got to the scenario 3 in Easy Racer where you have to race 10,000 concurrent things, the macro doesn't work because it's a runtime sized thing, and the macro
compile
works.
time size.
Well, the 10,000 is
Well, your problem required runtime sizing, but the macro says you have to explicitly say, here are all of my tasks.
Here are all my tasks.
Yeah, it was not made for the
It's not
dynamic
made. Yeah, exactly.
thing that you wanted.
So then we had to find a different approach for that particular one. But it was interesting, like, the macro is super helpful when you're in the constraints of what they've designed it for.
Right.
And I don't think that a macro could do what we were trying to do because it has to be run at compile time.
Yeah, it's. I mean, like when you look at the sort of the initial use case for the macro is, I have a variable argument list. Where Rust goes, well, we don't do that. You have to have everything at compile time. But the macro can actually handle that. But then so the idea is it's like, okay, it writes the code for your multiple different arguments, but then the compiler goes through and it says, all right, I know everything at compile time. So yeah, that's the kind of Rust philosophy is we got to know everything at compile time.
Yeah. So yeah, any other thoughts or learnings before we go on to structured concurrency?
I don't know. This was a very good week for me. I felt like I moved forward significantly.
Nice.
It was really nice to have everybody around kind of working on the same thing.
Yeah.
So yeah, it's a good experience.
It's fun. So Bruce has been exploring structured concurrency, and I was trying to get the Easy Racer Rust stuff working this week, which is structured concurrency oriented. And maybe we should start with what is structured concurrency. You want to take a stab at it?
Sure. Yeah, it comes from, the reason for the structured term is because way back, like in the 60s, some of the computer scientists started noticing that all the go-tos produced crazy, unmaintainable code. You didn't know where you were going to end up with.
The spaghetti.
Yes, the spaghetti. And so the idea was, okay, what we should do is move to putting everything in functions. Of course, the functional programmers knew that already. But that way, you have a single entry point and a single exit point. Even if you do early returns, you're still exiting at this single point. And that way, you have a scope. And the scope allows you to say, all right, you build things, we can make sure that they get all cleaned up. Everything, we drop the stack pointer for all the stuff that you need. Everything that you do gets cleaned up as you exit the function. So we have small scopes all over the place instead of one giant scope where we're jumping all over the place. So that's where the go-to considered harmful. And then Nathaniel Smith wrote, a number of years ago, wrote this blog post called Go Statement Considered Harmful. And I think he was specifically talking about the Go statement in the Go language, because you just say, go, fire off a function. And then the function's off there running. When does it ever get collected? How do you get the result? How do you cancel it?
You've kind of lost the linear flow.
You basically lost. You're just firing it off
back into go-tos. Which,
very similar to jumps. And the reason that they had to fight their way out of it is because so many people were coming from assembly language programming, and that was just how you did it. You didn't write all these nice little neat functions. You just jumped, and so they had to be pushed into using functions. And now that's kind of the standard way of thinking of things. Well, we write functions everywhere. So what this blog post suggested, and I don't think he was the first one to come up with it, but he made it as clear as possible, is that, we need a kind of a different kind of a scope. And so we create a scope, we create tasks within that scope, and then the scope guarantees that those tasks are finished before we exit the scope. And so that's kind of the foundation of structured concurrency. But there's some other things which are not completely clear to me. It seems like you also need a reliable cancellation mechanism, and a reliable error handling mechanism. And Python has, I mentioned the cancellation stuff, but it also, in the most recent version, has added something called exception groups. So it's something that is treated like a normal exception, but it can actually hold multiple exceptions within it. Because if you fire off a bunch of tasks, they could all fail, or multiple ones that fail. And if there's only if the first exception is the only one you hear, then the rest of them get lost. And so that was why it was necessary to add this feature in Python. But
so the task or the error group, what was it called?
Exception group.
Exception group allows you to have these different things concurrently, and then aggregate the errors across all of the things that fail can come back into an exception group.
And it seems like that has to be inherently connected to structured exceptions, because the exception group is what comes back from the scope that is managing the exceptions. Yeah, I just realized that this moment. It's like, okay, that's got to be tied to that exception scope that is creating those tasks, because who else are they going to report to? And it has to be to that scope. So yeah, I would say that both cancellation and error handling almost have to be an essential part of structured concurrency.
Yeah, and I think what structured concurrency tries to do is say, all right, a given function is not enough to model the things that you need when you're in a concurrent world. But how do we avoid the go-to spaghettiness? And we have to be able to have a bunch of things running concurrently and get back the results from those things and the errors from those things, and cancel things when needed. And so it seems like it was like, okay, a function doesn't give you the cancellation, the error aggregation, all that stuff, and so we need another concept there, and structured concurrency gives us that concept. One of the things I've wondered about with structured concurrency is, we call it structured concurrency, but what is the structure of it? And the only thing that I've seen is a hierarchical structure, where you have something that owns children essentially, but then those children can have other children and so on. So you can create a hierarchy if you want to, or you can keep it a single depth tree. But the hierarchy with having a parent and children is the only structure that I've seen for.
I would argue that what's in common between a function and structured concurrency is scope. So it's like, I'm creating a scope in both cases.
Yeah.
And the structured concurrency thing is like, it's a different kind of a scope.
Yeah.
And then when you start looking at these things, and you look at Rust and you look at its lifetime, and you go, oh, the lifetime seems like it's maybe a different kind of scope as well. And I think that's what it comes down to. It's like, we humans.
It's all about scope.
Yes, we humans can only handle a little bit of stuff at once, and so we have to make sure that that's clean and independent, so that we can reason about it. And then, so by creating these scopes, we achieve that.
It must all be about scope, whether it's function. The way that we avoid the spaghettiness is by scoping things, and in the case of structured concurrency is scoping with cancellation, concurrency, and error handling.
And when you look at, way back when, I don't know if you remember Modula, the language Modula 2. Well, that the whole evolution there was the idea of modules, which is another kind of scope, and Rust has those. We saw that with, you can have your library code, and in the same file you can create a module which is just for tests, for example. And it's a different form of scoping. I guess it's what the compiler sees, something to do with that.
So in the Go statement considered harmful article, he introduces his own framework, which was for Python, I think, right?
Trio.
Right. And their abstraction was the nursery.
Mm-hmm.
So that's the
scope.
The nursery
That's
is
the
the scope.
Yeah. And then so you create a nursery, and then each time you create a task, you create it from that nursery object. And then Python itself changed, so its async IO library has a task group, and that
which is like the nursery,
which is basically the same thing,
but ultimately just a scope.
But the thing about the task group is that it also manages the exception groups.
Mm-hmm.
So and I wrote a blog post, I think the last one I wrote, where I looked at that and I said, oh, so async IO, the standard Python library, has this structured exception handling that it works with its task group, but Trio doesn't. I mean, because it almost has to be part of the language. So it seems like the async IO library is more useful than Trio can be. And so I'm not sure. That was the question I left.
To the language support for the exception group.
Right. So I'm not sure my result was, I think I want to use the task groups because it has this better support. Mm-hmm. And I'm not even sure if Trio or any of the other third-party libraries, I suppose they could probably catch up with it, but I'm not sure. Anyway, it's there now, so.
And we, a week or two ago, did get the Python Easy Racer async IO stuff all working.
Yes,
so that was nice to see. So I think for structured concurrency, the kind of primitive that I've seen across now many different languages is the idea of a nursery or a scope. Mm-hmm. And the way that it gets used is you create your scope and then you add tasks into that scope, mm-hmm. and then you determine what you want to do with those tasks that are now in this scope. And so the two typical ones are a race, which is often called a select. And the select says, as soon as one task in this scope completes, either with an error or with a value, then cancel all the other things in that scope and pass that one thing out to your consumer. And so that select is what we used in many of the Easy Racer ones, because a lot of them are race-based structured concurrency challenges. And so select seems to be pretty universal for structured concurrency, the idea of the scope and then being able to do a select. The other approach, once you have your things in your scope, is a join, is what it's called in Rust. And I'm trying to think of
most
other
languages
names.
have a join.
Yeah, and so the join says, run all these things and just give me back all of the results and exceptions from all of those things. Mm-hmm. And so those are kind of the two, I think, kind of primitive things that you can do once you have a structured concurrency scope.
But what structured concurrency, I mean, normally you would, like without structured concurrency, you would create a bunch of tasks and then you would put a join to at some point, you would basically artificially create your own scope that way. So what structured concurrency does effectively is it quietly puts its own join in at the end of the scope.
Yeah. Mm-hmm. And in the case of the Python one, we did have to, in I think some of the scenarios, do the join, but then manually manage cancellation of the tasks. So we were doing a race on top of a join, and I don't remember why.
What?
But what we would do is do our join, and then as soon as we got one of the things in the scope to complete, then we would cancel all the others. And so we were kind of doing a manual select or something like that.
Because was there not a select in async IO?
There was, but there was some of the scenarios where it didn't work for us, and I can't remember the details on why it didn't work. So then we had to kind of do our own select.
Okay.
Yeah. We had to essentially create our own select implementation that worked the way that we needed it to.
So in Kotlin, I mean, because this is the first place that I came across the idea of structured concurrency was in Kotlin. When we do structured concurrency, you of course know what that means. That was the implication, and so, which I didn't. And so now I'm wondering, I mean, now if I went back and looked at it, I'd probably have a much better idea of what was going on. But did they also handle cancellation and errors?
Yep. Yeah,
Okay.
so coroutines in Kotlin do handle both cancellation and error management. So if you call a coroutine and it throws an exception, it is exception based, but if you throw an exception, then that will cancel your other children that are in that same scope. And so yeah.
What if you get multiple exceptions?
I think it depends on the implementation of select or join that you're using and what happens there. I'd have to go look at it, but
Okay.
yeah.
Yeah, I didn't have those questions in mind when I was initially looking at it, and now I go, oh, here are the things that you need to have to have a task system that actually works effectively and doesn't drop things on the floor.
Yeah.
Got to have cancellation and reliable. You don't lose either cancellation messages or any of the exceptions.
Yeah. Yeah, and so with the Rust structured concurrency one, as we mentioned, we were using select for most of the scenarios are a basic race. And so it was pretty straightforward. We make our request to the server, we do 2 of those concurrently, and then we do a select, and the first one that comes back is the winner, and we return it. And that was all pretty straightforward with the Tokio select macro. But then there's one scenario, I think it's scenario 9, where we have to do a bunch of concurrent requests and aggregate the results, and we use the Tokio join for that one. And then the 10,000 concurrent request race, where you're racing 10,000 concurrent requests, we weren't able to use the select macro as we talked about. And what we ended up doing was we had to have some way to kind of track the progress of these 10,000 requests and then be able to get the result out. And so we found in Tokio there's the multi-producer single consumer channel, I think is what we use, MPSC, and that allowed us to make our 10,000 concurrent requests. When one comes back, we put that in the channel. So we push to the transmit side, the result to the transmit side. And then we, outside of all that, our 10,000 concurrent requests, we can just wait for something to come into the channel. And when something comes into the channel, then we return it. And I think managed through the lifecycle stuff in Rust, it automatically then cancels the other 9,999 who were the losers essentially in that case. And so we didn't have to manually do any cancellation or anything. It was just all automatic.
Yeah, the contrast between cooperative multitasking and preemptive multitasking is that when you have threads or processes that are preemptive, that means that they can be interrupted at any time, which means that trying to do correct cancellation or error handling or anything becomes either really difficult or impossible. I definitely came across things that said, oh, just don't write any code that can't be canceled at any time, can't be terminated. In fact, they use the term terminated because it's very heavy-handed. And so it seems like only with cooperative multitasking do you have the ability to, easily, correctly cancel and correctly handle errors.
Yeah.
So that's a different benefit than I was thinking of when you go back and look at these other things. It's much. I think it's why we've had some libraries that don't do that correctly, is because traditionally when you've got threads or processes, you just kind of have to go, well, either you have to be a very clever, careful programmer and probably you still won't get it right.
Yeah.
Or just write your code so carefully that it can be stopped at any point. You can never you can never hold a lock because you could be holding a lock and then your task is dropped, and then everything is anybody else who's using that lock is screwed. So it's very
Yeah, I think the resource safety piece is really crucial in the world of structured concurrency. Is you have to have a way to safely cancel things that can clean up any resources that thing is holding on to. And I think in all the structured concurrency stuff we've used, there definitely is that like cancellation, resource safety handling happening. A lot of times in our cases underneath the covers, because what we have is a connection to the server which needs to be cleaned up, and so the actual HTTP client library is the one that is seeing that the thing is canceled and then doing the cleanup of closing the connection for us. So we didn't have to, in the case of EasyRacer, do much of that on our own. It was handled correctly by the HTTP client library.
Right.
But we validated that, yeah, sure enough, it is doing the right thing. On cancellation, it's closing the connection.
The nice thing about cooperative concurrency is that you have these known suspension points. And so the compiler can look at those and go, all right, I know this is where I need to store the necessary things so that the task can be suspended. And that's also why it can be such a small thing, why you can have, hundreds of thousands or millions of tasks, because each of them doesn't have to store the entire stack frame because it knows where you're suspending. And that's true with cancellation. That happens at those suspension points if it's automated like it is in Python, of course, if you do it yourself. But in both cases, the scope of everything means that like in Rust, things get dropped, and that's where that cleanup happens for your server connection. Yeah. Everything that's in scope gets dropped when you return from it.
Yeah. Yeah, so the scenario for this one that we did in EasyRacer, where EasyRacer tries to validate that you're doing this correctly, is you race two connections, but one of them needs to have a 1 second timeout. So you open the connection, you wait a second, and then it needs to close before the other one wins the race. The EasyRacer server won't let you win the race until you've correctly done that timeout.
That's the rules, that you set up.
And so in the Rust version, we just wrapped our request with a timeout, which is part of Tokio, and the timeout did the correct thing. It knew that there was a task that it needed to run and start, and then timeout cancels that task, and then that closed the connection, which allowed the other connection to win the race. So that was all verified to work and pretty straightforward in Tokio in Rust. So that was nice.
So Rust does do threading. So that makes me wonder, what's the cleanup story in that case?
Yeah, we didn't play with the thread stuff in Rust. We were on Tokio, which is all green threads, fiber based, and so it's doing all the management of actually executing stuff on threads for you. And we didn't dive into how that works, but I do remember there was a great blog post about Tokio's scheduler, which has some pretty at the time had some pretty significant advancements for doing fiber-based scheduling onto threads and all that. And doing it efficiently and alleviating things like header-line blocking and a lot of the problems that you often run into with a naive simple scheduler. They did some impressive optimizations and automatic management around, which then inspired Xeo's in Xeo 2. The Xeo 2 scheduler was I think pretty inspired by Tokio's scheduler for how the actual scheduling of tasks works. So.
Interesting.
Yeah, I didn't know that.
Yeah, there was a talk, I think it was by Adam on the Xeo team, about the inspiration for Xeo 2 scheduler and how they learned a lot from the Tokio scheduler.
Yeah, I have written something using threads, but that was embarrassingly parallel.
Yeah.
And it just ran to completion. I had no worries about cleanup or errors or anything, so I haven't really experimented with that at this point, but now I'm curious.
seemed like a lot of the Tokio APIs mirror the thread-based APIs, and so maybe it wouldn't be too hard to take what we did and do it on top of threads and see if there's any real difference or anything. But yeah, so we continue to learn about structured concurrency and different approaches. Definitely seems like the commonality is the structure, having a scope that you put things in, the cancellation, the error handling, the resource management, all that stuff seems to be pretty common. There are one thing that I do like in the world of Scala around this is that there are some higher level APIs for structured concurrency that I haven't seen built in some of the other languages and frameworks that we've worked with. So, for instance, if you want to do a join essentially, but take only all the successes in Scala Zio, there's a collect all successes par or something like that, and that will just you give it your list of essentially tasks, and it will just give you back the list of all the things that successfully completed. And you can certainly do that with a join, but you have to do some manual stuff after the fact, because the join is just going to give you back the errors and values, and so then you have to filter out the errors. And we did this one in the Rust one where we had to manually filter out the errors, and it wasn't too hard to do, but it's certainly nice to have some of the higher level APIs on top of this stuff.
To be fair, we didn't go looking for crates that might do that, and
there's very well
possible.
Could be a crate that would do a collect all successes par on top of the Tokio join. So definitely could exist. We didn't. You're right.
No, we didn't look. We were just trying to solve this problem, which was fine. But now I'm curious, because a lot of times when you go, gee, I wonder if this exists in Rust, it typically does. Like there's a whole lot of Python libraries that if there's a library you like and you go, wonder if it exists in Rust. Very often it does. There seems to be a lot of back and forth between the two communities. Somebody even called it, they said, I know Python and Rust are best friends now.
Nice. Yeah, any other thoughts on structured concurrency?
There will be, but not right now. Still figuring it out.
Continue exploring that. And the Easy Racer repo is up on my GitHub, James Ward Easy Racer, and with all the implementations, there's now
different languages:
Kotlin, Scala, Rust,
Go.
Python, Go, Swift, Elm. That's been a fun place to explore this stuff.
Yeah, that's been a good learning experience.
Yeah. Cool. Any last thoughts?
No, it was a good week.
Yeah, it's been a fun Rust developer retreat.
Yeah, it was. It was great.
All right. Well, thanks for being here.
Yeah.
Look forward to more.